So today what I want to do is to talk about this new data streaming platform powered by Apache Kafka. And I'm going to talk about some of the recent innovations we have been doing in this space. If you are new to Kafka, right, this is actually one of the most popular open source Apache projects out there. It's used by hundreds of thousands of organizations across the globe, across industry, including pretty much every Silicon Valley type tech companies you have heard about, and the majority of the largest Fortune 500 companies in the world. Some of you may have heard this technology was originally started at LinkedIn. We invented Kafka to solve the problem we were observing at LinkedIn. So this is actually the data problem LinkedIn had around that time. At the top, you will see LinkedIn has this tremendous growth in terms of the amount of digitized information being generated. And a lot of those different, this digitized information is not recorded in a single system. It's actually recorded in multiple of those systems because the developers want to use that preferred way of storing the data. At the bottom, what you will see is there's also a tremendous growth in terms of number of places where all those information need to be leveraged. This includes some of the data services LinkedIn has been adopting, but a growing number of those are those microservices LinkedIn has been building. So the observation LinkedIn had around that time is just recording those information in a data store doesn't really generate value for LinkedIn. Those data only generate value for LinkedIn when it's actually being leveraged by all those downstream data services and microservices. And a lot of those leverage need really to happen in real time, because if it doesn't happen in real time, the opportunity of leveraging that will be passed. So that's the situation LinkedIn has. But surprisingly, around that time, there actually wasn't like a good infrastructure to achieve LinkedIn wanted, because around that time, there are two primary systems people have been using. One is various kind of databases, but those systems are really designed for data at rest. They are most designed for recording the data first and then worry about how to leverage that later. The second type of system a lot of places have been using various messaging systems. But the thing is with those messaging systems is a lot of them, they don't scale to the amount of data digitizing information LinkedIn needs to accommodate for. Also, they are only designed for transient. So because of this, LinkedIn's data architecture grew to something like this, right? There's a lot of ad hoc point-to-point connections between those data sources and downstream systems. As you can see, it's becoming pretty messy. So that's why we designed Kafka. So what is Kafka? Well, we designed Kafka as a more modern data streaming platform. So we reason about the data in this platform as events. So you can publish those events in real time, and you can subscribe and take actions on those new events in real time. And it's designed to scale so that it can truly accommodate for all the data LinkedIn had. With Kafka in place, we completely eliminate all the point-to-point connection. All the data sources can integrate that data directly into Kafka, and all those downstream systems, including those data services, the microservices, can just make a subscription to all the data LinkedIn has and get a new feed in real time. So what we create is opportunity for LinkedIn to take actions on every business events happening within LinkedIn. So this significantly accelerated the innovation speed at LinkedIn. Fast forward to today, this data streaming platform based on Kafka is even more relevant because every enterprise is seeing the problem LinkedIn had. Every company is seeing a growing number of amount of places where data will be generated. And every company is seeing more and more places where data need to be leveraged, including data systems and then applications they have been building. And more recent technology advancement, such as cloud and generative AIs, are adding more of those data sources and the places where data needs to be leveraged. So just like LinkedIn, with Kafka, we provide every enterprise with the opportunity to take actions on what's happening to their business. So Kafka is now sort of becoming this standard for this data streaming platform. So what is it? Well, at a high level, what it has is a set of open APIs and protocols. With those open APIs and protocols, we were able to build an ecosystem around Kafka. So this picture tries to show that. In the middle, this is actually our storage layer, where we can store the data as streams at scale in a reliable and durable way. And we build an ecosystem around the integration layer. So we have this connector framework that allows all those popular data sources and the data sinks to be integrated with Kafka. Another layer we have built is the processing layer, because once you have data in Kafka, right? If you look at how people are building applications on top of Kafka, a lot of those are event-driven applications. They will take the raw data in Kafka and try to derive some new views out of it. As part of this process, often they will need to do some kind of transformation of the data. This could be doing some kind of projection, filtering, a little bit data enrichment through joins, window-based aggregation. So to make that event processing easier, we have built multiple of those event streaming processing engines. One is called Kafka Stream. This is actually meant for Java developers. It can be more embeddable. But another framework is getting popular is another open source project called Apache Flink. It provides some higher level abstract through streaming SQL that allows the applications to build this kind of event streaming processing much easier. So together, we have this data streaming ecosystem based on this set of open APIs and protocols, as well as the rest of the ecosystem. We have been continuing innovating in this data streaming platform. In Kafka, we have this process called the KIP, or Kafka Improvement Proposals, where we are proposing new improvements for how we want to evolve Kafka and the surrounding systems in different aspects. As you can see, there's a lot of things going on, and we have also a lot of future ideas how we want to take these systems. For example, recently we have gone through a big process of changing the control layer of Kafka from zookeeper-based to a built-in raft-based consensus service. This will give us much better efficiency and scalability. We have been also improving our group consumption model so that it can be more resilient and more lightweighted on the client. In the future, we also plan to add some of the traditional queuing support in Kafka. But today, what I'm going to do is just to talk about two of the recent innovations we've been doing in this data streaming platform. The first thing I want to talk about is related to the cloud. In the early days, right, one of the pain points people in terms of like adopting Kafka is really in terms of operation. If you're familiar with Kafka, you will know, managing a distributed system like Kafka is not easy, right? You have to worry about configuration, monitoring, logging, upgrading, balancing the data, right? To do this, we really need a team of experts, right? Which is not often affordable for most of the enterprises. But cloud completely changes that. With cloud, now people can build Kafka as a service in the cloud. So then the service provider will be the operator of the system and can take care of all the things that I mentioned earlier. And our user can just focus on the usage of the system. This is actually a much better model of consuming modern distributed software. But providing a fully managed Kafka service in the cloud is actually more than just taking the existing Kafka code, right, putting it in a container and running in the cloud. To really build a good managed service, you actually need to do a lot of work for it to be cloud native, to adapt to the cloud environment. So the first innovation I want to talk about is just one of the recent changes we made in Kafka to make one component of Kafka more cloud native. So this is about how we store the data in Kafka. Right? If you're familiar with Kafka, you will know this is actually how Kafka stores data today. When you run a Kafka cluster, you will have multiple of those brokers, right? Each broker will have some local storage. And all the data in Kafka will be distributed right, among all those local storage attached to those brokers. So this is the traditional way how Kafka stores data. Now, what's the issue is that in the cloud? Well, there are a couple of issues. The first issue is on the storage cost, because Kafka is designed as a real-time system, right? To deliver that low latency experience, you really need to use a little bit like those high-end low latency storage, right, to store your data. But for a lot of users, they actually want to keep a bulk of the historical data in Kafka so that they can do replay of the messages, so that they can do bootstrap. So if you only have one type of storage, you end up having to pay those high-end storage for both your recent data as well as your historical data, which drives up the cost. The second issue is in terms of elasticity. Because the storage is coupled with the broker, right? Which means you can't easily scale the computation needs independently from the storage needs. And when you need to scale, there's a lot of local data you need to move around, which adds time and as well as consumes a lot of resources. So what we did in Kafka is recently we have completed a kit called kit45, which added the tier storage support so that it can be more cloud native, that's more adaptive to the cloud storage capability. So in specifically, what we did is instead of just have one type of storage, we'll have two. We'll continue to keep the recent data in this local type of storage so that you can have this low latency experience. But for the bulk of the historical data, we can choose to archive them to a remote object store. And today, most of the cloud vendors have those object store that's pretty mature, and it offers pretty good cost in terms of pricing, and it also provides pretty good throughput. So by integrating this tier storage capability in the cloud deployment, we have changed how Kafka will be storing the data, as you can see in this picture. So what's the benefit of that? Well, the first thing is we have improved the cost efficiency a lot, because we only need to use those high-end local storage just for a small portion of the hot set data. But the bulk of the data will be stored in a much cheaper remote object store, which reduces the overall cost. The second benefit is by doing this, we have completely decoupled the storage needs from the computation needs, which means they can be scaled out independently. And when you do need to move things around, but when you add in more broker, there's actually a lot less data you need to move around, because it's only the local portion of data that's need to be moved. The bulk of remote data is always globally accessible. You don't need to move them. So this is just one example how sort of a cloud native architecture evolution would help of running these fully managed services like a Kafka in the cloud much better. But offering this like tier storage is just like one step to make Kafka more cloud native. At Confluent, we have built a cloud native Kafka engine, which we call Cora, which does a lot more. So in addition to tier storage, it has things like automated data balancing, handling degraded storage, optimized network, various resilient redundancies across region or across AZ. We have some of the self-validation. The end result of that engine is actually a much higher quality of fully managed service in the cloud. So you can use it and you can trust that it will do the best things for you. And it also can reduce the cost a lot. It can offer a high quality service as a much lower cost. So if you're interested in more details of that, we actually have a recent paper on the Quora engine in this year's very large database conference, and we actually won the best industry paper award for this. So I'd encourage people interested in this to check this out. The second this is the first innovation I want to talk about. The second innovation I want to talk about is related to the integration, collaboration between Apache Flink and Kafka. So if you are new to Flink, right, this is pretty becoming a standard way for people to do stream processing, and it's often used together with Kafka. And there's a lot more detail about that. I think the next talk actually will talk a little bit more in detail about Flink. But the reason why developers choose Flink is because it scales. It has pretty rich language support, including streaming SQL, and it offers both the unified processing for both batch processing as well as stream processing. So this is a common processing pattern you would do when you run a Flink job, right? You will take some data as streams from Kafka, and you will try to derive some new states. And then once the state is ready, you'll be try to write that state to a Flink store. But you also want to write the changes, right, about those states to Kafka, so that you can inform those changes to the downstream systems. Ideally, in the Flink job, they really want to have the rights to the Flink store and the right to Kafka to be atomic, so that they can support this exactly once semantic. That actually would be the ideal world. But today, in reality, because Flink store is a separate system from Kafka, right? If the writer fails in the middle, you actually can leave things halfway in between. Maybe some of the data is only in Kafka, right, but not in the Flink store, or vice versa. It's very hard to reason about the exact one semantic with the current state. So how do we solve this problem? Well, the conventional way of solving this atomicity rights, right, to two separate systems is through what we call this two-phase commit. So here's like a quick refresher how it works. So the way this works is you first, if you have multiple participants, right, in this system, you first want to queue up the writes to each of those participants, but without actually committing to either of those. Then you go through this two-phase commits. In the first phase, this is the preparation phase. There will be a coordinator which will ask each of the participant to prepare to commit for all the data you have accumulated in each of those participants. Once every participant has acknowledged, you go to the second phase, which is complete. The coordinator will commit data if all the participants said yes in the preparation phase, or it will abort this transaction if one of the participants says no. So this is how the standard way, the two-phase commit to handle this atomicity rights right across multiple systems. So what we want to do in Kafka, we want to take this idea and to add a capability that enables Kafka to support this kind of two-phase commit protocol, so that external systems like Flink can take advantage of that to build the exact one semantic. So let's see how this works. So some of people may be already familiar with Kafka. Will know Kafka already has this transactional support. So what you can do is, you can create a Kafka producer, you can start a transaction, you can publish a bunch of records, right, to multiple topic and partitions, and then after that you can call either commit or abort, and Kafka would guarantee all those records, right, would either be successfully committed in Kafka, or none of them will show up in Kafka. But this existing transaction support is not enough to support two-phase commit. It actually has some gaps. The known gap is in terms of dealing with those outstanding transactions when the producer fails. So if a producer fails, right, you have some outstanding transactions that's not committed yet. So the current Kafka transactional support always aborts those outstanding transactions. For example, if you recreate a producer instance, right, the new producer instance always abort outstanding transactions before it can start any new transactions. And if you don't start a new producer, those outstanding transactions will just automatically get aborted after timeout. As you can see, those outstanding transactions, when it's being used together in coordination with external systems, we don't always want them to be aborted, right? So that's the gap we have in the existing system. So the way we fix that is through this KIP proposal, which is KIP 939. What we do is we made 3 changes roughly at a high level to make that two-phase commit ready. The first thing is we are adding this two-phase commit config. Once you set it, it will disable the existing auto abort capability. The second thing we added is the ability to do a prepare phase. So we added a prepare transaction phase, which makes all the outstanding data ready to be committed, but not yet committed. And by the end of this call, we'll return a unique ID for this outstanding transaction, which can be used by external system for the coordination. So if the external system has a handle of this unique ID, once it's ready to complete the whole system, it can make another call called complete transaction with that transaction ID. And then to cover this complete transaction, we'll use the passed in transaction ID to decide whether the outstanding transaction should be aborted or actually committed. So let's see how this works in practice with Flink. So with this capability, we can change the Flink flow to like this. This will be the normal flow when you run a Flink job. So if the once the Flink job is ready to write to both systems, right? The first thing we'll do, it will write the log changes into Kafka, of course, with two-phase commit enabled. The second thing is Flink will call prepare transaction in Kafka to make sure those pending data is ready to be committed and get back this unique transaction ID. In the third step, Flink will write whatever state changes it needs to do into its own store together with that transaction ID we just obtained in the second step in an atomic way. Flink has the capability to do that. And once this step is ready, then Flink will go back to Kafka and say, okay, please commit that transaction. So this is normal flow, which looks pretty simple and reasonable. But the tricky part, of course, is in the failure case, because that's when some of the duplicates could be introduced, right? So what happens when the Flink job fails in the middle, right, between these four steps? Well, when a Flink job fails in the middle, there could be two scenarios. So let's visit them one by one. In the first scenario, it's possible that the Flink job fails right after the second step. So it has prepared the transaction in Kafka, but it wasn't able to take that transaction ID and write a new state, right, and the transaction ID into its own store. So in this case, you will see the transaction ID, the last transaction ID in the store still is from a previous committed transaction, which is different from the last open transaction in Kafka. In this case, the right decision to do in this case is to abort this transaction, right? Because to make that consistent, you need to get rid of this guy, which is not in the Flink store yet. In the second scenario, it could also be that Flink job fails after the third step. It actually has taken the transaction ID from Kafka and has already written that transaction ID together with the new state into the Flink store. But just before it tries to commit that transaction in Kafka, it fails. As you can see in this case, what we'll see is the transaction ID in the store and in Kafka will match. And in this case, we should really complete that pending transaction. So that's exactly what we'll be doing in terms of the recovery of the Flink failure. So if a Flink job fails, when it comes back, the first thing it has to do is to go through this recovery logic. The way you do recovery is the Flink job will first go to its store to retrieve the last transaction ID. And once that, it will use that new API we added in Kafka to call complete transaction. Under the cover, this complete transaction will look at this passed in transaction ID, compare that with the last transaction ID in Kafka, and see if it matches. If it matches, it will do the commit like here. If not, it will do the abort. So with this, it can truly provide this atomicity between the two systems, like Kafka and the external Flink data store. So the idea is, once Kafka finishes this kit proposal, the Flink community will have its own proposal to integrate this capability in Flink so that it can achieve this exact once processing between Flink and Kafka. This is actually a pretty exciting capability from both communities, as it will provide this anticipated exact once semantic during stream processing, which is important. Okay, so these are a couple of the innovations I want to share. Just to conclude, what we have seen is this Kafka-powered data streaming platform is becoming mainstream. And Kafka and its ecosystem is becoming the standard, right, for people to do this data streaming. And a lot of the enterprises are building newer event-driven applications on this platform so that they can provide better user experience, drive efficiency, reducing risk, gaining new business insights, all within just a couple of short seconds. So we'll be continuing the innovation in this data streaming space to satisfy all those upcoming enterprise needs.